So we're going to do a few more inverse Laplace transforms where the form may not be obvious. So let's take a look at this one. So we have the inverse Laplace transform of 1 over s squared plus 2s plus 5. Now we're used to seeing this as an s squared plus k squared in the denominator. But can we rewrite it so that perhaps we have a shift in the argument for s, so an s minus a squared? And the answer is yes. We just need to complete the square. So here's the trick. We're just going to group the s squared plus 2s together, and we'll move the 5 outside the parentheses. Then we just carry out completing the square with the part inside the parentheses. So we look at the coefficient for s, which is 2, divide it by 2 to get 1, square 1 to get 1, and that's what we'll place there inside the parentheses. So we put the plus 1 here. Now we can't add 1 without subtracting 1. So that's all we're doing here. We're balancing it. So we just subtract the 1 from the 5 to get a 4. So now this looks a little more like something we're used to seeing, where it's like s squared plus k squared with the k in the numerator, but with a shift of s minus a, where here our a would be negative 1. In this problem, k is 2. Now that means we would need the k in the numerator as well. So we put the k up there, we put 2. Now we can't multiply 2 without dividing by 2 out in front or multiplying by a half. And then we have it in the right format. So the part in the brackets here, the inverse Laplace transform of that expression, we just take the cosine of 2t, and we've shifted with an a equals negative 2. So we have to multiply by e to the negative t. And of course we have the 1/2 out in front of it. So that's how we take this inverse Laplace transform. So if you start out with an expression that you're not quite familiar with, try completing the square. And more times than not, we'll find that we can find the inverse Laplace transform that way. Here's another one. Again, it's the same type of problem. We have an s squared plus 12s plus 61 in the denominator. So let's complete the square. So let's pull the 61 outside of the parentheses and work with s squared plus 12s. So we take the 12, divide by 2 to get 6, square 6 to get 36. So we add the 36 there, subtract the 36 there. 61 minus 36 is 25. And of course, this expression is just s plus 6, the quantity squared. It's just the number you get here is what you place here. All right, now, this time, we have a 25, which is 5 squared, so our k is 5. So we'll need a 5 in the numerator. We'll multiply by 5, divide by 5 in front to cancel those two. Now, our s minus a here tells us that a is negative 6. So we have 5 over s squared plus 25 in the general formula that we're used to working with. That would be inverse Laplace transform of the sine of 5t, but we've shifted with our a equal to negative 6. So we have our 1/5, our e to the at, where a is 6 minus 6, and then sine of 5t. So all we've done is shift this sine of 5t by an e to the minus 6t. Well, this one, again, we're just kind of looking at problems that we haven't seen before. So what if I have the inverse Laplace transform of 1 minus s divided by s squared plus 1? Now that does look like a s squared plus k squared, but we haven't seen a numerator like that. So, but here's the trick. We could rewrite this fraction as 1 over s squared plus 1 minus s over s squared plus 1. And now we know the inverse Laplace transform of each of those expressions. That's just the sine of t, because k is 1, and this is cosine of t, k is still 1. So in that case, just rewrite it and get two inverse Laplace transforms that you know. What about this one? Again, it's the same idea. Just work with the s squared plus 6s. Take half of 6 to get 3, square the 3 to get 9, so we need a 9 there. We place the 9 there. And of course, we have to subtract the 9. 13 minus 9 is 4. This expression is just s plus 3, the quantity squared. And our numerator happens to be s plus 3 as well. So this shifted term here matches. We'll see in a minute one that doesn't match. Now, here our s minus a term tells us that a is negative 3. Here it's like, this is like an s over s squared plus k squared, so we're looking at a cosine of kt if we want to compare it to the formulas we know. So here our k is 2, so we have the cosine of 2k for our case. We've shifted by negative 3, so we have to multiply by e to the minus 3t. And if you look at the table of Laplace transforms, you'll see those formulas in the second column of that table. So what happens if that shift in the numerator doesn't match? So we'll take a look at one of those. So here, instead of having an s plus 3, we have an s plus 1. So we need an s plus 3 in the numerator. So this is the same problem as before, but we changed the numerator. Now if I need a plus 3 there, I can make it a plus 3 by adding a 2 to that expression. Well, if I add a 2 there, I have to subtract a 2 from it. So I just basically split it up into two different fractions. So this first one has the s plus 3 like we had before. This one has minus 2 over s plus 3 squared plus 4. So this is the form of an s over s squared plus k squared. This is what we found before, the previous problem. This one has the k over the s plus 3 squared plus 2 squared. So this is just the sine of 2t, and it's shifted by e to the minus 3t. So that's how you can modify that numerator by adding the number that you need. If you add it, then you have to subtract it. So that's how you handle problems like that.